So when we last were together, we talked about this idea of circular motion. So what we want to now look at, what we're going to be investigating, is uniform circular motion. So just going around a circle in a uniform manner. So what that means is that the angular velocity is going to be constant. So there'll be no change in the angular velocity. So you might think, well, hang on, if there's no change in the angular velocity, how do you get acceleration? Okay. Well, the magnitude of the linear velocity will be constant, but that does not mean the acceleration is going to be constant, because there will still be a change in velocity, even though the velocity is constant, because the direction of the velocity is changing. So let me just draw this up. There's the circle. So a particle is going to move from A to P with a constant angular velocity. So I'm actually going around clockwise in this case. The acceleration will be the change in velocity. But at A, velocity is going off as if it's a tangent to A. So it's going off in that direction. At P, let's call it V dash. Now the size of V dash would be the same, but the direction is different. So if I was to draw up a vector diagram, so I've got V going in that direction, V dash going into that direction. So the difference between the two must be the change. So I must have gone down V. There must have been this third vector that would get me back to the end of V dash. And that must be the change in velocity. So how we change. So we ended up at the end of the V dash vector. Well, unless that theta happens to be, I guess, 60 degrees, then the actual change in V is not going to be the same as V and V dash. So all right, well that triangle of vectors would actually end up being similar to triangle OAP if you think about it. Because remember we said the magnitude of V and V dash was the same. And the angle of the centre is theta. So you've got side, angle, side. In our actual triangle, well, the two radii are going to be the same, and the angle at the centre is theta. So again, side, angle, side, but you've got a proportion rather than congruency there. So we know they're going to be similar. So there's those two triangles. So if I look at the ratio of the sides in the similar triangles, so the size of the change in velocity over the length of that chord AP must equal V over R, whatever those magnitudes are. So I'll play around with that and get that the change in velocity will be V times AP over R. Now we know acceleration is the change in velocity over the change in time. Now this V times AP is not equal to 0. So there is going to be an acceleration in this. So change in velocity over whatever the change in time is. So I've subbed in for delta V, the V times AP over R. So there's a formula for acceleration. Now, if you think about circular motion, that direction, going around in circular motion is like an infinite number of change in directions, because you're just continually changing direction. So the actual change in time is very close to 0. In fact, it may as well be 0 because it's going to be instantaneous, that change. So we want to look at the limit of what happens as that change in time approaches 0. Now, if that change in time is approaching 0, then the length of the chord AP will be approaching the length of the arc AP. Because if there's, if it's time, you haven't really moved anywhere for them to get a difference between the two. So as the time approaches 0, those distances would be the same. So now I could write it as like this. Well, the acceleration is the limit as that change in time approaches 0 of V times the length of the arc AP over R delta T. Well, we know distance equals speed times time. So the length of the arc AP will be whatever that linear velocity is times the change in time. So if I sub that in for the length of the arc, now this might start looking familiar for those of you from your science days and those that do physics, because now on the top you'll see, well, the delta T's actually cancel. And I just have V squared on R. There's now nowhere to substitute in delta T. So in fact it's always going to be V squared on R. So the acceleration in uniform circular motion has magnitude v squared on r. It's always directed towards the centre. So if you look at the direction of my red vector, that change in v, that actually would be going towards the direction of the centre of the circle. Good news, you don't have to derive it like that, okay? We can just quote. But that's where it comes from. So we can do it using vectors. We can get this. It's not just something we've pulled out of thin air. So the acceleration involved in uniform circular motion is acceleration is v squared on r. If we were using angular velocity, then it would end up being a equals r times omega squared, because remember velocity is r times omega. So if you substitute that in for v squared, do some cancelling with the radius, you'll get r times omega squared. So it all depends how it's being mentioned, whether the velocity is in a linear velocity or you've been quoted an angular velocity, which one you would use. But of course we're interested in forces. So the forces that are involved in this problem, now that may seem familiar to you, I hope. There's the force, mv squared on r, which you hopefully have seen in science. So there's the force, or of course it could be mr omega squared. That is the resultant force of circular motion. So it's not actually a force, it's the result of all the forces act together. All those changes in direction, all of those acting together comes up with this resultant force. So when we're solving circular motion problems, instead of going mx double dot, we can go mv squared on r, or mr omega squared. I said they wouldn't ask you to derive it the way I just did it. Here's how you would probably derive it. I'll take the 2003 question. So particle, constant angular velocity, they've given us angular velocity of omega. And then they've broken up the components into horizontal and vertical, just like we would with projectile motion. So the horizontal displacement, r cos theta, y is r sine theta, which really is just the parametric coordinates of a circle. And theta is omega times t, so the angle would be omega times t. Show that there is an inward radial force, or they like using fancy words, of magnitude mr omega squared acting on the particle. So they want us to actually prove this force of mr omega squared. Right, so let's put it on the number plane, and we'll give it its parametric coordinates, r cos theta, r sine theta, and actually work on the two components independently. So x is r cos theta, y is r sine theta. Differentiate those with respect to time. So on the left hand side, displacement becomes velocity, dx dt. On the right hand side, I can't differentiate it with respect to time because my variable is theta, so I need to use implicit differentiation. So I'll differentiate it with respect to theta, multiply by d theta dt. But of course we define d theta dt as the angular velocity. So I've substituted in omega for d theta dt. And so we get that the horizontal component of velocity would be minus r omega sine theta. We do the same thing for the vertical. Only difference is now I have cos theta instead of sine theta when I differentiate, but again d theta dt becomes omega. Alright, there's the displacement and the velocity equations. Let's get acceleration. So now I'm going to differentiate acceleration with respect to theta. But remember, we're talking about constant angular velocity. So omega would be constant. But differentiate the sign with respect to theta, we get minus cos theta. We get cos theta, but it was minus sine theta. Again, times the theta to t, I've got to do it implicitly, which now means I have minus r omega squared cos theta. Simple harmonic motion, if you look at it. Circular motion is just simple harmonic motion, but it's in two directions at once. It's moving simple harmonic motion horizontally and simple harmonic motion vertically. So if you were to sort of imagine it was doing it, the circle was going horizontally. If you were to just look at the circle, what you'd be seeing is a particle going backwards and forwards, like simple harmonic motion. Yes, it's actually moving in a circle, but if you couldn't see the circle, all you could see was the object, you'd see it moving in simple harmonic motion. And it actually doesn't matter where you look at the circle, being symmetric, at any point that would happen. So horizontally we end up with simple harmonic motion, minus omega squared x, and vertically we end up with simple harmonic motion as well, minus omega squared y. Well, we want to come up with the resultant. So if I create a triangle and say horizontally the acceleration and vertically those two components, let's come up with the actual one, then acceleration, the actual value of it, I can do using Pythagoras. So it'll be the horizontal squared plus vertical squared will give me acceleration squared. And so we end up with, for acceleration squared, of course, x squared plus y squared with the equation of our circle, x squared plus y squared equals the radius squared. So acceleration, take the square root of that, and there it is. Acceleration is r omega squared. So that's how I guess they would be expecting you to do it, was by breaking it up into its horizontal and vertical components, much like we do with projectile motion. Now, it also said to prove it was an inwards radial force. Oh, a force then is mass times that, so there's the mr omega squared. Well, how do I know it's going inwards towards the centre? Well, that angle then would be the inverse tan of y double dot on x double dot. If I sub into that, I get inverse tan of y on x, which is, if you go back to our original diagram, well, yes, the inverse tan of y on x must end up being theta, the angle coming from the centre. So the direction of this vector must be going in towards the centre of the circle. So yes, there is a force, mr omega squared, acting towards the centre of the circle. Now, to be honest, I think that's the only time I've ever seen them ask you to derive it. But if they did want to do it again, well, that's how we'd do it. Okay, let's apply it to a problem. So our good old satellite, there it is going around the Earth. Of course, gravity's not G out there in deep space. Well, it's not that deep, I suppose. It's just above the Earth's surface. But they've told us it's AM on R squared. A is just some constant. We're going to show, well, that there's the radius that our satellite is travelling at. So there's good old Bob. Circular motion, the resultant force, that's what I've drawn there. It's always going towards the centre of the circle. I'm going to assume, for convenience sake, that I'm taking the point in the circle when it's just directly above me. So it makes it a pure, vertical one. So I have mr omega squared. I mean, when you think about it, somewhere in the arc, it's straight above someone on the Earth, because they're always going to look up and go, oh, there it is. Yeah. But the only force would be the force due to gravity, which again would be going down towards the centre of the Earth. So AM on R squared. So the resultant force, which is mx double dot, but in circular motion, the resultant force is the centripetal force, as we call it. So mr omega squared. And that will be AM on R squared. Now, the masses will cancel, but we can rearrange that little formula, and we end up with R cubed is A on omega squared, and so there we have it. R is the cube root of A on omega squared. So really, even though it's going in a circle, it's still exactly the same as what we saw with resisted motion. See, all motion can be broken down to be a straight line. Even when we're moving in circles, we can break it down to be a straight line. Our string is 50 centimetres long. We know it will break if we put a mass bigger than 40 kilograms. So 40 kilograms is the actual biggest it can hold without snapping our string. We're going to put a 2 kilogram mass on it, and we're going to revolve it around in a circle above our heads because it seems like a fun thing to do. Whee! Well, what's the fastest we can go without breaking the string? Well, there's my bob hanging on the end of my string. It's just hanging down. Now, what's happening there? Well, I'm going to say my resultant force is going straight down for this problem. What other forces do I have? Well, I have the acceleration due to gravity, or the force due to gravity. there is another force. Okay? Whenever you have a string attached to an object, the resistive force in the opposite direction is what we call tension. You might have heard the term tension in the string. So tension will always go up the string, if you like, away from the object, up the string. So whenever you've got an object attached to a string, you're going to have this force of tension. So our resultant force, taking into account the resistive force of tension, is mg minus t. Now, what have they told us for this problem? Well, 0 at this stage is because it's just, remember, it's handling it okay. It's just sitting on the end of the string. Nothing's happening. So there is no acceleration. It's not moving. It's just staying on the end of the string. So I know that 0 will be mg minus t. That allows me to work out the maximum tension it could hold, because we said the heaviest mass we could put on it was 40 kilograms. So if I put that 40 in there, and the force due to gravity is not changing, so 9.8 for G, I know the maximum it can handle is 392, and the units for force is newtons. So 392 newtons is what it can handle. Now, newtons is also kilograms per metres per second squared. That's why it's easier just to say newtons. But if you see newtons, then we know the mass has to be in kilograms, length, distance, whatever, has to be in metres, and time is in seconds. Right, so we know the string can handle 392 newtons. So what happens now? I'm going to get that same thing. I'm now going to spin it horizontally in a circle. So it's now performing circular motion. The resultant force then must be going to the centre of that circle. So if I'm spinning it on a string to the left on my little object, because I'm looking at it when the bob's over here on the left, so the resultant force must be going towards the centre, the left. And we know that will be mr omega squared or mv squared on r, whichever one we want to use. There will be tension in the string still. Whenever an object's attached to a string, tension. Gravity in this time, nothing, because it's horizontal. And gravity is a vertical force. So now my new diagram gets me that the tension is actually equal to the resultant force, because there are no other forces there. Okay, well, we know the maximum tension it can handle is 392. So let's sub in. 392, I've put a 2 kilogram mass on it. The radius is the length of the string, 50 centimetres, but we need it in metres. So that's 0.5. Just need to make omega the subject. So there we go. 2 root 98 radians per second would be the fastest I could spin this around my head without the string breaking. So we're going to play with a few circular motion questions.